Okay, just some background things. First is don't forget we've got the Canvas homework that's due for this lesson. It'll be due next class. This is so weird that I've got absolutely zero feedback. Let me try one more time. Testing 1, 2, 3. That is so weird. I just want to be sure. Thumbs up with you guys. One last time on sound. Excellent. Okay. Canvas is due next class. We're going to have another, if this goes well, we'll have another video next class. We have, besides this one, I think that there's 2 other videos I'd like to shoot, and then we'll have videos for every single lecture. The lab is due today, and we're switching over. We'll talk about this more, but we're switching over our next lab into a do-it-yourself lab, which will require more work. So just as a heads up, that'll be a challenge. Yeah, let's begin. So now let's begin. What I'd like to do today is to firstly review what we've discussed with FIR filters from last time. We'll talk about 0 locations for FIR filters, and I'm going to give an FIR and IIR construction information. And last, we'll talk very briefly about C code to implement your filters in a microcontroller. Because I can't see your faces while I'm writing on this whiteboard, and I can't read the chat line. If you've got questions, just unmute and say them. Okay, so last time we talked about an FIR design method. And in particular, what we said is that you first find an impulse response and make it even, because if it's even, if it's symmetric around the 0 point, that means it's going to have 0 phase. Because if it's symmetric in the time domain, the DTFT is going to be purely real, and a purely real DTFT it's all magnitude, it's no phase. So just as an example, we've got something like there's our first attempt at making an H of n, and this is going to be, and this one is 0 phase. And then we'll delay it. We'll delay it by D is equal to n over 2. I need another color to make it a little bit more obvious what I've done. But there's my delayed signal. And we've delayed it by here 1. And then the last step is to truncate. So it's only non-zero in that region. So with our example I just gave, we truncate, and now this is an FIR, linear phase filter. So all you need is the prototype definition for a zero phase filter, and you can make it FIR. And you can make it FIR as exacting as you want. So if you've got a prototype for H of n that extends off in an infinite number of points in either dimension, you can choose to have a very accurate representation of it by choosing a very large n and then delaying it by half of that, or you can choose a rough approximation, but something that's easily and quickly computable with a small n, and then we'll have very little delay, but it won't be as perfect to whatever original H of n you had designed. And then the other thing we talked about, we did talk about this design method, and then we talked about the 4 types of FIR filters. And in particular, we said they can either be, the H of n can either be symmetric or can be anti-symmetric. And if it's symmetric, you can have an even order or an odd order. And then the same thing for the anti-symmetric. And the types are 1, 2, 3, and 4. And for all of these things, we have a phase function that is going to be equal to be a decreasing it's going to be linear phase, which means it's going to be decreasing with n over 2. That's our delay. And then it's either going to be plus 0 or pi, depending upon if our filter, if our H of n is symmetric or anti-symmetric. That matters less. What matters more is that because it's linear gain up here, our delay is going to be n over 2. And our G just means it's G is short for group delay. There's several ways you can define delay, and group delay is the most common. And that means if you put in a cosine of any frequency, what you'll get out will be the exact same cosine, just delayed by n over 2 samples. Okay, last time. Any questions on that? Great. So we've done this. Let's go on to 0 locations of FIR filters. Cole, tell me about the pole locations of an FIR filter.
If I am correct, is it where the uh I want to say it crosses the x-axis, but I don't think that is correct. Is it like when the denominator is a certain value, like 0?
Let's go back to what. Let's go back to an example then. H of n. Let's graph this. I want you to really feel confident about this. I want you to see this. Let's see the exact same example we just gave. So here's our H of n. First, let's just check. Cole, you're still in the hot seat. Is this an FIR filter's impulse response?
Yes.
Yeah, definitely, because it's finite length. And is this, to continue on, Cole, is it zero phase?
No, it has phase.
It is not zero phase. Is it linear phase?
Yeah, it's linear.
It's linear phase because it's symmetric right around here. So because it's symmetric around n equals 1, it has a delay of 1. It's symmetric around n equals 1, and therefore it has a delay of 1, and therefore its order is equal to twice its delay is equal to 2. Okay. And because of that, we can write out our h of z just by inspection. And Ben, what's its h of z? And Raj, you'll be next. Take a look at its h of n. What's its h of z going to look like? Let's say this is 1, and let's say this is 2, and this is 1.
Z plus 2z to the -1 plus z to the -2.
Almost exactly right, except for the first one. The first one is just 1 times z to the 0, which is just 1. But the rest of what you said is right. The second is 2 z to the -1 plus z to the -2. Okay. If you had a plain z in there, that would be something that would be not causal, would be something out here. So here's our h of z. So now, Raj, here's our h of z. I guess I could have just as well written it like that. Tell me about its poles. Where do you see its poles?
There's no pulse here because the denominator doesn't go to 0.
Yeah. So at first blush, anything that's FIR has nothing in the denominator. The denominator is 1, and so the denominator is always 1 for an FIR. And so you might say, hey, there can't be any poles. There can be poles, but only in one place. Cole, tell me what h of z is when we evaluate it at z equals 0.
At z equals 0, it is
Uh-huh.
1.
Sure about that?
Yeah.
1 plus 2. Z to the -1 is just going to be 1 over z, right?
No, man, I understand your question.
You got it?
Yeah.
Yeah. So at z equals 0, it blows up. So what Raj said is almost 100% right. There are no poles in an FIR filter except at z equals 0. And from what we talked about last class, here's our complex plane. Here's the real part of z. Here's the imaginary part of z. And we're going to put in this value of z, wherever I say, into our h of z above. So here's our unit circle, just to make it simple. And our h of z here, it can have poles at z equals 0. Now, here's the cool part. Those poles at h equals 0 do not affect your frequency response at all, because as you go around your unit circle, if you look at the height of what h of z is as you go around the unit circle, it's always equidistant from that pole, so it doesn't affect those frequency response at all. You can have any number of poles there, and in fact, you have as many poles there as you actually have an order of your circuit. So, in fact, you can have as many poles there. One more time. In fact, you have as many poles there as you have the order of your system. So for this particular system that we gave above, there'd be 2 poles right there. And then we'd have to solve this equation here to figure out where the zeros are. So going back to what we started in the beginning, the poles P can only be at z equals 0. Shoot. Let me try that again. The poles P can only be at P equals 0 at the origin. If they're any place outside of the origin, it's not going to be an FIR filter because then our denominator won't be 1. But there's a lot we can talk about our number of zeros. There's a lot we can talk about our zeros. Firstly, the number of zeros is going to be equal to the order of the filter. So in the example that I'm giving, Ben, what's the order of this filter?
Second order.
That's right. N equals 2. Even though it's length 3, it's second order. Now here's where it gets a little tricky. The zeros, I'm going to call them Z, always appear in conjugate pairs. And that's true not only for FIR filters, but that's true if we have a real impulse response. And we always have a real impulse response. Always, no matter if it's IR or FIR, anything. In an undergraduate response, we always have a real impulse response. If it's FIR, IR, or if it's any kind of filter, it's always real. And even in graduate school, I don't recall ever seeing a complex response in the time domain. And so that's the same thing as saying that the pole 0 plot will be symmetric around the horizontal axis, always. Whether or not it's 0 phase, whether or not it's FIR, always. And just as an example, that means that if there's, say, a pole, a 0 rather, at 2 at an angle of 30 degrees, there will also be one at 2 at an angle of minus 30 degrees. So let me give a short picture of that. So here's the real part. Here's the imaginary part of Z. We're in the unit circle. I'm drawing where the poles and zeros are of our system transfer function. And what I'm telling you is that if there is the only poles can only be here. And if there is a 0 here, it means there's got to be one here to make it symmetric top and bottom. If it was IIR, the same would be true for its poles too. If there was a pole out here, say, there'd be one down here. So that's a very general thing that's not only true for FIR filters, but true for anything. Here's where it gets tricky. The zeros also appear in reciprocal pairs, and that's a new concept for us. And that, when you see that, it means it's linear phase. And as an example of what I mean by that, I mean that if you've got a 0 at 2 at an angle of 30, you also have one at 1/2 at an angle of 30. So if we've got one here, here's our 1/2 at an angle of 30. It means we also have one out here, both 30 degrees, but now the magnitude has a reciprocal value. However, because it's of the first one, they appear in conjugate pairs, that means we also have one here, and we also have one out here. So just adding a single 0 off the unit circle means we've got to actually add 4 orders to this thing. How about if we had one, let's use up next, Raj. How about if we put one right here? How many zeros would we have to add in order to keep this thing linear phase?
So that's negative, or that's 90 degrees, or 180 degrees, and then negative 180 is the same place. And
That's right.
because so it would add, and then there would just be one like half the distance from there, still at 180 degrees, however.
That's right. Well, it's 1/2. Well, it's at the reciprocal of 1/2. So 1 over 1/2 is 2. So the other one would appear all the way out there. So sometimes, depending upon where you put your pole, let me try that again. So sometimes, depending upon where you put your 0, you might need to actually add 4. Some places you might need to add 2. And then some places, let's try one right here. Cole, if we place one here, where else do we have to add one, if at all?
Well, the reciprocal of 1 is 1, so I don't think we would have to add 1.
So you're done. The first rule is that it's conjugate paired already. And then the second rule is that the reciprocal pairs itself. So some places you can add a single 0. Some places you can have to add 2 zeros. And some places you have to add 4 zeros. Let me give an example. Oh, so big picture, what we're talking about is this is always and this is only for linear phase. Let me give an example. And Ben, you're up next. Here's our real part of Z, our imaginary part of Z. And I'm saying you're going to start off with zeros. You're going to start off with a pole here, and a 0 here, and a 0 here, and a 0 here, and a 0 here. And Ben, walk me through where I have to add 1 0 or 1 pole here to make it linear phase.
You would have to add a 0 at the 90 degrees at 2 and a 0 at,
Okay, wait a second. 90 degrees up on this axis?
oh, I'm sorry, at 0 degrees at 2.
Yes. So here's our 2, and that corresponds to this guy. Okay.
And another one at 135 degrees out at 2 also.
That's right. And that satisfies the linear phase part. But how about satisfying the always part up here?
You would also have to have it directly opposite. So at 180 degrees at 1 and 2, and then at
You only have to flip it vertically, not horizontally.
oh, okay. So then at halfway between 180 and 270, you would have to add one at 1/2 and at 2.
Yeah, negative 135. So here's our, so these are these guys. And then we've got one from up here that has to be added. And now we're set. So given where we started from, Raj, tell me what is the order N of this filter, of this system?
So we've got,
Shoot. Did not mean to do that. I was hoping I could just get rid of the 2 because I want to make it clear that there's only 1 0 there. Go on.
so we have, I know we have 2 orders just from the fact we have one at 90 and then we have the one right at 0. So those are orders by itself. And then there's a third order, which is at 0, but at a different, well, it's got a reciprocal. And then there's what looks like a fourth order with the ones that are reciprocated and conjugate.
So the way to find out what order it is to use this rule. Whoops, that's odd. Is to use this rule. Just count up the zeros. We got 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9. Just counting them up.
So we do count the conjugates and the reciprocals.
That's right. You count them all. If it's a 0, you count it. So now we know it's an order 9. What is its purpose? If you were to look at it, does it block low frequencies? Bacol?
I think that it. Hold on, give me 1 second. I think the lower frequencies are passed better than the high.
Well, take a look at what this is doing down here. Maybe if I fill it in, take a look at that guy. So when you evaluate, you can read off its DTFT by taking you can read off a system's DTFT by reading around this part of the unit circle. So here we're looking at omega equals 0, our low frequencies. Here we're looking at omega equals pi over 2 radians per second, our medium frequencies. And here we're looking at omega equals pi radians per second, our highest frequencies. So if we're looking at our low frequencies, we're right on top of this 0. It's another way of saying our H of Z evaluated right here at this Z of this Z equals 1, right? This corresponds to a Z equals 1. This corresponds to a Z equals J, and this corresponds to a Z equals -1. So H of Z equals 1 is on a 0. So therefore, H of Z is going to be 0. Is that clear, Cole, or not?
I thought to tell it's like based where the holes are to the pole. So it's like the ratio between it.
It's the ratio. That's right. And so take a look at what's in the numerator. The numerator says it's the distance from where we're evaluating at low frequencies to all of our zeros, and then divided by where we're evaluating at frequency to all of our poles. If we're right on a 0, though, we're going to multiply everything in the numerator by this 0. There's zero distance between here. Let's take a, let me give another simulation.
So it would get rid of it, is what you're saying.
It'll get rid
And
of
then
it,
it
but I
would
want
also
you,
get rid of the pi over 2, so medium frequencies.
that's right, exactly. So this thing will have a DTFT. Here's our magnitude of x of e to the j omega versus omega. And going around this circle, we start off with something that is going to be at 0. And then at pi over 2, it's going to be 0. And it's going to do something. It's going to do something like this. And then the 0, the pole rather in the middle, doesn't affect it at all. And I can't really tell exactly what it does more than that. Does that make sense to everybody, or is there anyone not sure about this? Would anyone like to see the demo about how to calculate, how to take a look at the pole zero diagram and from it read off the DTFT? Can I see a thumbs up?
Can we look at the demo?
Yeah, sure. Okay, so here's a demo. And firstly, let's see, should this be, can you see the demo? Good.
Yes, sir.
Should this be 0 phase, regardless of what you see in the right hand side? Should this be 0 phase? Should this be linear phase?
This is linear phase because of the fact that it has those reciprocals.
That's it. It's real. It's symmetric around the horizontal axis, and then it's linear phase because for every 0 here, there's one at its reciprocal location. So I'm going to graph now the linear gain in. I'm going to graph the linear gain. Give me a second. There we go. Okay. So here's the linear gain, and for this one, we start off. Let me show you those vectors. So to graph at low frequencies down here, we take the product of the distance as we sweep our frequencies around from wherever we're sweeping to all of our zeros, and then divide it by the product of the distance from wherever we're sweeping to all the poles. So as we sweep this guy around, you can see that the magnitude goes down because this line here is getting smaller and smaller. And eventually, when we're right on top of that 0, we're multiplying the numerator by 0. So the output has to be 0. And then it goes down a little bit when we get really close to this pole. And then as we get away from all the, I'm sorry, let me try that again. It goes down a bit as we get close to this 0. And then as we get away from all those zeros, it goes back up a little bit, but not up as high as it was at low frequencies when we're away from all of them. If we wanted to move one of these zeros close to this, close to a low frequency, we could. And now we've killed that low frequency because at low frequencies, it's really close to this 0. And in fact, as we increase our frequency, it stays really low because we're multiplying by this small value. If we wanted to enhance our frequency, say at high frequencies, we could put a pole right there. Here's a pole really close to there. And now you can see what it did to those high frequencies. And we can move that pole anywhere we want to. Here it is for low medium frequencies. And now when we get close to that low medium frequencies, we can see that our response just shoots up because we're dividing, we're multiplying by all the greens, but then we're dividing by these purple things. And when we get really close to the pole, we're dividing by an incredibly small number, so it shoots up to infinity. Thumbs up from everybody? Awesome. Okay.
I just had a quick question about the reciprocals.
Shoot. So this is not, and so just to be clear, this is definitely not now a linear phase filter. It is an FIR filter. Oh, it's not even FIR because I've got this pole here. Let me get rid of this pole to make it FIR. Now it's FIR, but it's not linear phase. Go ahead, Raj.
If we have the reciprocals, when we get to a certain point, is it purpose of them that they like can't like the product of them just cancels out to become one?
Say that one more time.
So, like in our example that we did, like when we wrote down 2 angle 30, and then
Yeah,
we
Let's-
had also 1/2 angle 30.
let's just try that right now. And we'll get rid of these guys. So this looks to me like it's, I need to, I don't have the screen space to make it exactly, to make it 2, but I can get kind of close. That looks about rightish to me. Let me do it even easier. Let me say 45 degrees, and then the reciprocal of 45 degrees is going to be, this is at square root of 2. This is at 1 over square root of 2. So the reciprocal would be square root of 2, which would be about 1.4. So it'd be about there. And now let's just take a look at I'm graphing the gain over here, but I'm going to change it to graphing the phase. And look, the phase is almost perfectly straight. And if I could get these things right on that line and at reciprocal pairs, this little bit that's not right would go away. The fact that it splits by 180 is just a phase difference. This minus 180 is the plus is same as plus 180. So this is really linear phase going right up. Okay, Raj, talk.
My question was, so this is at 45 degrees.
Yeah.
If we got to 45 degrees, then would the distance between our 0 at 1/2 45 degrees and then, or at that point, and then it's reciprocal, which is, would that just cancel out to make 1? And then we're only working with the distances from the zeros at negative 45 degrees?
Let's see. So here we are right there, and we've got, and we don't have, it does not cancel out. If you want it to cancel out, what you want to do is not put zeros at the reciprocal pairs, but put poles at the reciprocal pairs. Let's see if I can just do that. This is a more advanced topic, but let me try it. If I could do this exactly. There we go. I can almost do it exactly. If I could do it exactly, Raj, if we could balance out zeros and poles at reciprocal pairs, we could create a unity gain transfer function that would be completely flat in frequency at all frequencies, at every single one. And that, although that would have a unity gain, although that would have a flat frequency response, the phase would be anything but, shoot. Even though it's flat, the phase would be, here's the phase, would definitely be very nonlinear. Does that sort of answer your question?
Yes, sir.
I'm hand waving here a little bit because we're getting into an area I don't want to, but staying back in the area that I do want to, this will have a phase that's almost perfectly linear. And if I could get these things right on, I could eliminate that little hump that you see and make it exact. Oh, that's really close. And make it almost perfectly flat. All right. Couple of other interesting things about this. Let's take a look. Let's take a look at the one that I just gave before. Let's take a look at this. And I have to think about this for a second. We'll do one here. One out here. This should be pretty darn close to linear phase. That's the phase diagram I've got on the right side. And I'm obviously struggling with it. I think this is about as close as I'm going to get. This is linear phase. What frequency is? Let me do an even easier one. I'll do one here, one out here, and we'll get rid of the others. How about that? It's a little ugly. I've got a knee in there someplace that I can't quite get rid of. That's pretty close. Okay. So we've got this linear phase filter. Who is up next? Cole. What is its order?
Fourth order.
It's fourth order. So Ben, how much should it delay an incoming sinusoid? Fourth order linear phase filter. What's its delay?
Is it delayed by 1?
Not if it's fourth order.
Oh, delayed by 4.
Almost 2. Let's go back to the let's go back to our whiteboard for a second. So here's our whiteboard. Remember how we made this? We made the linear phase filter to begin with. We took a zero phase filter that was symmetric. We delayed it, and then we truncated it. And you can see that this is our second order filter, and it's been delayed by 1. And if it was I'll just do a quick example here. If we had a much bigger, a much longer filter, this one is a n equals yeah, that's right. So this one is an n equals 3 filter. Oh, now I've got to think about this one. However much we delay it, we want to, it's twice that order. Oh, what am I saying? This is let me try that again. I'm losing it. This is an n equals 4th order filter. It's 5 long. It's n equals 4. It has 4 zeros, and so therefore it has a delay of 2. And you can see why it's symmetric around that too. Does that make sense, Ben?
Yeah, that makes sense now.
So let's go back to this guy, and this is a n equals 4 filter because it's got 4 zeros. It has it's got an impulse. It has an impulse response. Let me show the impulse response. It has a impulse response of problem is I'm giving it a steady state impulse, so I can't show it. It has an impulse response of length 5, an order of 4. It has a delay of 2, and as we feed it different kinds of frequencies, we can see it has this delay of 4. Here, if we feed it a 0 frequency, and get rid of all those little lines, feed it 0 frequency, it's a constant input. So you can't tell what its output. You can't tell that it's delayed by 4. But let's increase our frequency a little bit. Remember, we're always putting in a cosine in. Now you can see it. We're putting in a cosine in. Our first output looks like it's been shifted by 180 degrees. But in reality, here, this input right here, it's been shifted by 4, and this is where our cosine begins. It's just been shifted by 4. It's a shame it's discrete, Tom. I can't show you that. If it was continuous sum, you could actually see it's a perfect shift by 4. But I'll just have to tell you that it's a shift by 4, not a shift by 1. If we have a different kind of signal that's a little bit slower, we might be able to see that. And I'm going to have a hard time showing that with this. Anyway, the thing I want to get across, let me head back. The thing I'd really like to get across is that you saw that if we want to increase our order by 1, we could not necessarily do it by just adding a single 0. When we added a 0, if we want to increase here's an example of a linear phase FIR filter. And we want to increase the current N, which is equal to 4, by 1. Where do we put the 0? Raj? Can we put a 0 here to increase it by 1 and have it stay in FIR and equal an FIR linear phase filter?
Sir, Raj is in the bathroom.
Up.
But if I had to guess where to put it, it would have to be at like omega equals 0 or omega equals pi.
That's it. You can only put it at one of these 2 locations. These are the only locations that will let you add 1 0 without adding multiple. And that means that the moment that we want to increase this filter, and this particular filter happens to be a type 1 filter, the moment we want to increase it by 1, we cannot have we have to have either something that stops low frequencies or that stops high frequencies. In other words, we can no longer have a band stop filter, because it's going to guarantee to stop either low frequencies or high frequencies. So our locations of our zeros, when we're talking about FIR linear phase filters, are not completely arbitrary. And here are the rules for them. The rules is that if you've got a type 1, an existing type 1, 2, 3, or 4 filter, meaning that your N, your filter order, which is the same thing as the number of zeros, is going to be even, odd, even, or odd. The zeros that you have at Z equals 1 is going to be even, odd, or odd. And when I say even, I'm also including the possibility of having none. And we can make the same we can make a similar argument about zeros at Z equals -1. Here, though, it's going to be even or none, odd, even or none, odd. And that means that they're going to have some sort of limitations. So while there's no limitations on type 1, type 2 can't be high pass, because of this. You've got an odd number of zeros at -1, guaranteeing that there will be a 0 at that high frequency. Here, you can't have type 3. You've got the biggest number of limitations. No low pass, no high pass, and no band stop. And then type 4 can't be low pass or band stop. And that's why we talk so much in the very beginning about these different, that's why we talked last class about why there are these 4 types of FIR filters, why it's important to know the difference. Because if you need to have, moving over here again, if you need to have a high pass filter, it's not going to be just as simple as necessarily adding. If you've got a type 1 filter that's currently high pass, you can't necessarily just add a single order to it and have it stay a high pass filter. You might have to add 2 orders to it to have it stay a type 1 if you want it high pass. Make sense?
Yes, sir.
That was a we spent a little bit more time on this because we did a little bit more view than I was expecting. There's going to be more to this video that I'm going to add now. You're welcome to stay on if you want to. You're welcome to leave for your next class if you want to. It's going to be about 15 minutes. None of it is nearly as intellectually difficult as what we've already covered. We spent a lot of time reviewing stuff to make sure that we got this down. Now I'm going to give 2 just turnkey construction methods for FIR and IAR. And we actually talked about the C code implementation last class. Okay, if you'd like to go, you can go. And if you want to stay, you can stay.
So are we still forming up at 2 o'clock today?
Yep. We need to talk about the about this last lab. It's a little tricky.
Perfect.
Okay. So let's talk about briefly about IIR filters. Just as an introduction. The pro for them is that for the same complexity as an FIR filter, it gives a much sharper cutoff. So as an example, here's our magnitude of our DTFT. And a typical FIR filter here's a pi over 2, and here's our pi. This might be a typical FIR filter of order 20. But an IIR filter of order 5 might be much flatter in the passband, have a steeper knee, and have a more complete flat stop in the stop band, even though it's only a fraction of the order of the FIR. And because of that, because you can get by with a smaller order for the same or better frequency domain performance. I didn't say anything about time domain, but frequency domain performance. Therefore, it's faster to compute your output, given a steady stream of incoming input signals. So that's useful. It's also, the system is easier to design. Now, the above comment said that after you've got the system designed, it's faster to compute an output given an input, but it's also easier to design the actual system because you can use very traditional methods. I'm hand waving over that. You can go into MATLAB code and see how a typical IIR filter is developed. And I'm going to give you some example code below. But I am telling you, if you have to program a microcontroller to design on the fly a particular IIR fourth order filter, it's going to be much easier than the code you'd need to write in that thing to design an optimal equi-ripple fourth order FIR filter, especially because it wouldn't be a fourth order FIR filter to give you the same frequency domain response. You might need to design a 40th order FIR filter to get the same response. There is a big con, and that big con is that it is can't be linear phase. Can't be linear phase because if it's linear phase, it has to be finite length, and an IIR filter by definition is infinite length. And because it can't be linear phase, therefore it will distort a passband signal in the time domain. I mean, both will distort a signal that's not in the passband. If you're designing a low-pass filter and you're putting in a high frequency, both should kill that signal entirely. The difference is that if you've got a low-pass system that you've designed, and if you're putting into your system a low-frequency signal that should be entirely passed, maybe it looks like a triangle wave going in, the output of your FIR filter will look like a triangle wave like it should. The output of your IR filter, while fine in the frequency domain, will look completely messed up and not look like a triangle at your output. So if your time domain performance is important, you want to use FIR. If your frequency domain performance is important, you want to use IIR. And I want to give you right now 2 quick filter design construction methods to use. I'll give you one that only works for a second order FIR filter. And you specify your passband frequency and you specify your stopband frequency. And it's not perfect. I mean, if it was perfect, it would look like this, right? This is our frequency, and this would be our passband, and this would be our stopband. And what we're doing is we're graphing the magnitude of the DTFT of our filter, and it perfectly passes low frequencies and it perfectly blocks high frequencies. With an n equals 2, we're definitely not going to get that. With an n equals 2, we're going to get something that looks more like that. But the benefit of this is that you can design it on the fly, meaning you can use the system, program it into a microcontroller, and now have the microcontroller change what your filter is doing, the frequencies that it's passing or cutting on the fly. And by the way, this is not only for a low pass like I've just drawn. If your omega pass is up here, and if your omega stop is down here, then you'll get a high pass result. So let me tell you what the secret. what the secret is. The h of z is going to be of the form alpha plus beta z minus 1 plus alpha z to the minus 2. These two things have to be the same, right? Because it's linear phase. So all you need to know is the formula to compute alpha and beta. And I'll give that to you in a second. I'm going to delete this part out when I make my video. To define your alpha and beta, you solve this simultaneous equation, where if this is your matrix A and this is your unknown vector, and this is your matrix B, you solve that. To find your alphas and your betas, you use this. To find your alphas and your betas, you construct a matrix. This is your matrix A, your unknown matrix filled with your alpha and your beta values. You set it equal to your constant matrix B, and you solve that traditional matrix X, unknown matrix X filled with your alpha and your beta. To find your alpha and your beta, you construct this set of simultaneous equations, where this is the traditional matrix A, unknown vector X, and constant vector B. Solve it using matrix methods to find your alpha and your beta. Now, just like that will give you a computable on-the-fly FIR design that you can use in a microcontroller. Here's another method that instead works for an IIR filter. Now, it's only n equals 1, and our first version will only work for low-pass filters. But because IIR filters in the frequency domain are more powerful than FIR filters, this still gives a useful result. And the form of our filter in the frequency domain looks like this: 1 minus alpha over 2. That's just a constant. Alpha is a number that we'll compute in a second. That'll be a function of where we want our cutoff frequency to be. plus this, where we know our alpha is going to be a function of our frequency. It's going to be 1 minus sine of our cutoff all over cosine of our cutoff. And the text is an interesting derivation of how to get this. The text has an interesting derivation of how to create this formula, but the end result is that given any kind of low frequency, the text has an interesting derivation of how to get this result. But the point is that for any low frequency, still don't like that. The text has an interesting derivation of how to get this. The text has an interesting derivation of how to get this. But the important thing is to realize that this gives you a method to create an IIR filter that's quickly computable, and that the text gives an interesting derivation of how this filter was originally computed. But the utility of this approach is that you can put this into a microcontroller so that on the fly, you can derive a new transfer function to compute a IIR filter of any low pass frequency. Still don't like that. The text gives the derivation of this particular IIR first order filter. I find that less important than the result. And the result is that this gives you a method so that you can compute on the fly any arbitrary first order IIR low pass transfer function for any changing cutoff frequency. And you might think that it's very limiting, that it works only for low pass filters, but in fact, a simple alteration can make it work for high pass filters, because it's important to see that a high pass filter is just 1 minus a low pass filter. See if you can see that from the example we gave above. Here's our 1 up here. So if you take 1 minus that, you'll get something that looks like this. And while you could compute the high pass by just taking 1 minus this mess, with a little bit of algebra, we can simplify it, and it looks like this. The alpha is computed using the exact same method as described above. It's just the transfer function that's changed slightly. I'll rewrite that formula to find alpha just to make it perfectly clear that that hasn't changed. Okay. So it's So in review, today, we started off today we began by reviewing the 4 types of FAR filters from last class. So in review, we started off this class reviewing the 4 types of FAR filters from last class. We talked about where the zeros have to be constrained to for a linear phase filter. And then we discussed why we talked about what those 4 types of filters were. And then we talked about why we introduced the nomenclature for those 4 different types of filters, because not all filters can produce arbitrary frequency responses. And so sometimes if you want to make a filter more exact, you can't just simply increase the order by 1, you might have to increase the order by 2. We talked about how IIR filters are better or worse than FIR filters, better in the frequency domain, worse in the time domain. And then last, we brought it home with 2 real-world methods to design your own FIR filters and IIR filters that could be low pass or high pass for either one, and that you could dynamically recompute on the fly. Shortly, we'll learn a far, far better way using MATLAB to compute an arbitrary purpose filter and an arbitrary order filter. But unlike these 2 methods, the MATLAB system will have to be pre-designed. The system will have to be pre-designed. You won't be able to recompute its impulse response on the fly.